thanks. Okay, so we start 5 minutes late, okay? All right. So I'm going to talk about the growth of black holes and the host galaxies. And before I start, I want to thank my collaborators and colleagues, in particular my student, also Onakat Chatmabachak, whose work I'm going to present. And of course, I also want to point out my colleagues in the FIRE team. Okay, so given what you heard from Sandy and from Melanie, I don't need to elaborate on why studying the galaxy black hole kind of relations is important. Suffice it to say that these relations may reflect the co-evolution between galaxies and black holes, and explaining and understanding this co-evolution is a major part of galaxy theory. So I think there are two potential challenges that are associated with studying the galaxy black hole relations, and we heard about this a little bit in the two previous talks, I think. The first one is, I think that there is an observational challenge. Just from the observations, I mean, it's very difficult to infer some of these properties, in particular if you go to lower masses or if you go to higher redshifts. Of course, also measuring the black hole masses themselves is very complicated, and there are different methods to do this. Each of these methods have their own different biases, potentially, and challenges. And then finally, what we heard from Sandy before is that there is potentially not just one relationship that applies to all types of galaxies, but there are different relationships that hold for different galaxies. So, for instance, here I show the black hole mass to stellar mass relationship for elliptical galaxies and zeros in the nearby universe. And you can see it's a slightly superlinear good relationship. I think the slope is about 1.4 or something like this. And then what I'm going to do now is I'm showing you at the same plot where local AGNs fall. And these are typically more kind of later types. And they fall down there. Okay? So there's a clear difference here. Now you may argue, okay, maybe they're different in this kind of relation, but maybe they're still the same if you just plot the bulge mass at the bottom, and you would be right to some extent. But I think even in that particular case, there is still, I think, a claimed offset of a factor 2 or so in the black hole mass at fixed bulge mass. Okay. Then I think the second kind of challenge is the theoretical challenge. Okay. And I think Melanie made a great point where we saw the different simulations, also with Illustrious and Eagle and so on. Each of these simulations has a different, comes with different physics, with different physics to model the galaxy, and with different physics of modeling the black holes. And as I think Melanie showed quite convincingly, the results that you get do depend on these model assumptions. So a few of them, a few of these model assumptions are quite obvious, like do you put feedback in there and not, or what is the kind of feedback that you want to put in? But some of these are actually much more subtle. So for instance, where do you place the black holes in your simulations? Do you allow black holes to merge? How do you actually model how the gas is accreted onto the black hole? So the devil is here a little bit in the details. Okay, so I think my main points, my main takeaway from here is, first of all, you should always be very critical about the robustness of both the observations and the models, especially in this particular field. And then it's also, it is non-trivial to compare the simulations and the observations in a fair manner. So one needs to also be a bit critical there. Okay, so having said all this, I'm now essentially going to proceed. Okay, but keep these remarks in mind. So what I'm going to do now is I'm going to show you kind of results based on numerical simulations, essentially studying the black hole galaxy connection in numerical simulations. The sample of galaxies will be low to moderately massive galaxies over a large range in redshifts. Many of these galaxies are gas-rich and disky, so they have lots of cold gas with large good angular momentum. So I think one thing is clear, namely that I think Bondi good accretion is maybe not appropriate in this scenario. And also, essentially, with these host galaxies are maybe more akin to good AGN hosts than to a massive quiescent the early type galaxies. So the question is now, okay, if we don't use Bondi, how do we actually bring gas from the large scales to the supermassive black holes in the center of these galaxies? And what I'm going to use, what I'm going to talk about here, is essentially uses the analytical model that was developed by Phil Hopkins and Elliot Cordard a few years ago. And it's this gravitational torque-driven good accretion model. And the basic idea is that it operates at these small scales. Here at the large scales, let's say scales above 100 parsecs or so, or above a few tens of parsecs, you essentially would explicitly resolve the torques in the simulation. So you need to have a very high resolution simulation. And then the model essentially would operate on scales of below a few tens of parsecs. Okay? And an important feature of this model is that the black hole good accretion rate essentially scales almost independent of the black hole mass. That's of course very different from the Bondi good accretion rate, where it scales with the square. Now, if it scales with a high exponent, essentially with exponent greater than 1, you essentially have an intrinsic good instability. As the black hole grows, you get a higher good accretion rate, good grows more, and so on and so forth. And so if you have Bondi accretion, you essentially have to naturally use feedback to stop this instability and to self-regulate the black hole mass. In this kind of model, where the growth rate essentially is independent of the black hole mass, you don't have to do that. So you can essentially be perfectly fine with a model that has no black hole feedback. And the models that I'm going to talk about do not include black hole feedback. Okay. So the simulations are massifier simulations, which this is like a large suite of simulations that's part of the FIRE project. And this includes about, well, essentially a few dozens or so of zoom-in simulations where the primary halo has a mass of maybe 10 to the 13 or so solar masses at different redshifts. So these are here, for instance, there are few other good extreme halos at high redshift, and a few of the simulations are run down to redshift 0, but the majority essentially is at redshift 2. The numerical resolution is a few tens of parsecs. The baryonic mass is a few times 10 to the 4. And the time resolution is also very high. And the latter is important because the analysis is essentially done in post-processing. Okay, and as I mentioned before, there's no black hole feedback in here. In fact, in most of these simulations, there's no black hole there to begin with. Okay, so how do we go about this? Now, the process is very simple. You run your halo finder on your simulations. You create a merger tree for the halos. You find the center of the halos, and there are different ways to do that. You say, this is where my galaxy is, that's where my black hole will be. And then if the galaxy is sufficiently massive, let's say at 10 to the 7 solar masses in stars, you seed a black hole there, and you can seed it with different masses. The default is 10 to the 4. And then you compute the accretion rates based on the formula that I just showed you, and this uses essentially the properties of the galaxy in the vicinity of this black hole with imaginary particle that you place there. You may limit this to 10 times Eddington, for instance, the accretion rate, and then you go from one time step to the next, from one snapshot to the next, by integrating the rate and accounting for black hole mergers. Okay? So the first question is, how important is this on, let's say, the seed mass? Okay, so the default, as I said, is 10 to the 4, but we played around with a number of different kind of seed masses from 10 to 10 to the 5. And note that this here only goes to redshift about 3. Okay, so what you can clearly see, and the exact results dependent, is dependent a little bit on whether you have a cap in the accretion rate at Eddington or 10 times Eddington. But overall, if you go down to redshift 3, at that point there's essentially no difference anymore in your black hole mass. Okay, so you see, of course, a large difference at early times, because here you start from 10 solar masses, and here you start from 10 to the 5. But by the time you go to redshift 3, there is no difference anymore, meaning that if you want to use essentially black hole galaxy scaling relations to infer what the seed mass is, you have to go to very high redshift to do that. Okay, so you cannot do this below redshift 3 in this model. Okay, so let's look how the scaling relations look like. That's the plot. I want to remember you again. I want to remind you again that that the sample is more like AGN hosts. So I show you both like the traditional kind of scaling relations, more for massive ellipticals in the local universe, but also for some more recent kind of papers which focus more on AGNs or late type galaxies. And so what you should look at is maybe the redshift 0 and 1, which is like the local version. As I said, we don't have that many kind of data points at redshift 0. These are the gray ones here and there. But you can see that that if you look at the black and the red together, you know, there's decent agreement here. Here, not so. I mean, here maybe here, but then if you go to the extremely high velocity dispersion objects in local universe, then there's a mismatch, and maybe that's not totally surprising, because as I said, these are not really good kind of massive good elliptical galaxies. Okay. What's also interesting is that the black hole kind of stellar mass relation appears to be essentially independent of redshift. Okay, and that's not true, for instance, for the Witten sigma relation. So at a fixed black hole mass, as you go to higher redshift, galaxies seem to have higher velocity dispersion. Okay, so let's now look a bit more closely into this one here. And it's important, you know, why would one focus on this one? Well, it's obviously kind of much easier to measure the stellar mass at high redshift than it is to do, let's say, with a Bald-Studiz decomposition. And it's not even clear that at high redshift you can do that, or that this is a reasonable thing to do, because it may be that you know, kind of galaxies at redshift 3 or 4, they may not just be simple disk plus bulges, right? They may be much more complicated kind of train wrecks. All right, so let's look at this again. And now it's kind of color-coded according to kind of how many kind of snapshots and galaxies are in this given bin here in this two-dimensional kind of histogram. You should remember that this is essentially with a time sequence, right? So this includes all the different snapshots together. So it's not a snapshot at one particular epoch, but I showed you before that it doesn't appear to be strongly redshift dependent, so it's a kind of it's perhaps an okay thing to do. All right, you may think that it looks approximately linear, and maybe you're right, but I'm now going to try to convince you that there are actually 3 different good regimes here, 1, 2, and 3, okay? And you may think, okay, maybe Robert got crazy. I mean, this just looks like a straight line. Okay, so what I'm going to do now is I'm going to change the model very slightly. And what I'm going to do now is I'm taking out the black hole mergers. Okay, so everything stays the same. All I'm taking out is I do not allow the black holes to merge. And then it looks like this. So essentially, maybe a flip back and forth. There's no difference here and here. The only difference is in this regime 2. Okay, so this increase here is really kind of related to that black holes are allowed to merge. Okay, what can I do next? Well, let's say we also place the black holes kind of slightly differently. So at the moment they are placed at essentially the density centers, which typically places them, especially with a high redshift, in very gas-rich regions. Okay, so they can grow very good efficiently. Let's just place them at the center of mass of the halo. Okay, that will still be typically in the galaxy, but typically not in the most dense region, and see what happens. And the result is quite dramatic. The growth at very early times, essentially when the galaxies are low mass, is severely hindered, and the galaxies essentially they stay with their seed mass for a much longer time, and then they start growing. Okay. But again, there's overall this regime number 1, kind of regime number 2, and then regime number 3. Okay. So also maybe note that this end here really doesn't care about any of this, right? So I made all these changes. The final mass of these black holes is the same. All right. This looks very similar for the other scaling relations. I just show you an example here where I take the black hole mergers out so it's more clear. This is for the M black hole and bulge relation. This is for the, okay, this is actually, this is sigma here, sorry. This is good M sigma relation. And you see the same trend goes up, goes over, goes steep, and then it goes essentially linear again. Okay. Now, how do we would explain this? In this model, as I said before, the accretion rate essentially is independent of the black hole mass, but it scales with the galaxy mass within some characteristic radius. So let's just do a few simplifications. Let's assume that this here is essentially the galaxy mass, and let's also say, okay, it's approximately the stellar mass of the galaxy. Well, we just ignore the gas mass here. This is not entirely correct, but again, this is just a qualitative good analysis. Okay? So if we do this, then we can write the slope of the relation as just this, and then if you put this in here, we essentially have m star squared divided by this. Okay? Right, so now we can see what happens in different regimes. So number one is if the black hole mass is dominated by the seed mass, or if we change the, let's say, if you change from here, let's say we change the stellar mass growth, and if you then patch the solutions together, you essentially have like a pre-existing black hole mass. Okay, so that's the same regime. In this case, the slope will be very small, so we'll be close to 0. And that's what, of course, you see here. And that's also what you see when you go from here to there. And I comment on this in a moment. The other thing is, okay, so let's now assume that this here is actually dominated by the integral of this. Okay, so it's by the integral of this. Right? So it's just, then you just replace this with the integral of here. And now you can essentially put in different models. You can, for instance, say, okay, what happens if the stellar mass kind of grows with exponentially? Then you find a slope of 1. If the stellar mass growth is constant, let's say if you have a constant star formation rate, and most of the stellar mass is, most of the stellar mass growth is dominated by the star formation rate, then you get a slope of 2. If the stellar mass growth kind of declines, then the slope shoots up. And that's essentially what happens. So at early times, the galaxy grows very quickly, so you get a slope of order unity. Then the star formation rate starts to level off. So you now change the regime. You now have like a pre-existing black hole mass, and the slope gets flat. And then as the star formation rate declines further, the slope gets very steep. And then something interesting happens here at late times. And I think what happens there is that at that point, the increase in the stellar mass is driven by mergers. It's driven by galaxy mergers. Okay, so it's not by the star formation rate anymore. And then you kind of, again, in this kind of regime here, so you will have a slope of 1 to 2 at the very end. Okay, I think I'm out of time. That's what I guess this means. So let me just go to the conclusions. All right. So, okay, so I modeled the growth of supermassive black holes in post-processing with this gravitational torque-driven good accretion model, okay? The results are as follows. This model can reproduce the local scaling relations without black hole feedback. The seed mass that you put in leaves little trace if you look at redshifts lower than 3. You can also, in this model, would understand why black holes grow first, let's say slowly, and then, or let's say first they go linear, then flatten, then it steepens up, and then it goes of order linear, with again at later times. And yeah, and I didn't have time to talk about the last point, but what we find in the simulation is also that if you look at redshift 6, we have essentially, well, extremely massive galaxies, extremely bright galaxies with high star formation rates, but we do not have any supermassive black hole with a mass much larger than a few times 10 to the 7 or so at redshift 6. So now the volume is not that big, right? And our sample is relatively small, so you maybe would expect this, but I think this indicates that there is a large number of low luminosity quasars in very massive hosts at high redshift. Okay, thank you.
questions? First and then.
When you run hydrosimulation with black holes, you find that supernova feedback have a strong effect on the growth of black hole in a low mass end.
Mm-hmm.
How can you ignore that?
No, it's not ignored because we have the supernova feedback, of course, in there.
But not affecting black holes.
No, yes, it does.
How can you make a supernova affect the black hole in
Well, because it's done in post-processing, so you know how much gas is around the black hole at each given time. So the supernova feedback affects the gas distribution around the black hole particle that essentially, I mean, is virtually there. And so you compute the accretion rate essentially based on how much gas is there.
Why don't you consider it when you're thinking about it?
Excuse me?
Why don't you think about it when you try to understand what's going on? You didn't mention supernova at all in your considerations of what affects the shape of the growth. Why?
Oh, okay, okay, thank you. Yeah, so, I mean, this is, of course, is built in, right, in the simulations. But yeah, I mean, the feedback is there, and the star formation is there. And of course, this goes along with the stellar mass growth. Yes. Okay.
I'm wondering if you've made plots of the accretion rate distribution function as a function of redshift.
Yes.
And so, because that has been measured out to redshift 4 quite robustly as a function of stellar mass and star formation rate. So do you match those observations?
Well, we have not made the comparison. We have some of these. So we looked at the accretion rates. They're typically so high redshift. They're very bursty. Sometimes they go up to Eddington, but they're mostly kind of lower. And the later times they're essentially always lower, like it's at least 2 orders of magnitude lower below Eddington.
So, because what's observed is a very wide distribution that shape doesn't evolve very strongly with redshift. The normalization does, but the shape doesn't.
I don't have the plot, so I can't. Yeah, but it's a good thing. We definitely want to look into this. Yeah.
We have time for 2 more questions. So here and then in the back. Sandra Faber.
I didn't understand your rapid growth due to mergers phase.
Okay.
Because I think of when mergers are happening, the stellar mass increases, but since the scaling laws are sort of linear, the black hole mass increases proportionately too, so that due to mergers, black holes and galaxies tend to move along the scaling direction. And yet, you showed us when you leave mergers out of your picture, there's this vast
Right.
range of slope.
So what mergers are you talking about?
Well, that's what I want to clarify.
Yes.
Okay. So what mergers were you talking about?
So I was talking about black hole mergers. So essentially, you leave everything the same because I mean, it's simulations you can't change, right? So the galaxies merged and they changed the stellar mass. But what was turned off was essentially turning off the mergers of the black holes themselves. So essentially, you end up with a galaxy which has then many supermassive black holes, but they don't merge together. Okay, that's it's a free model. I mean, it's not what one would do, right? So, but
well,
it's
yeah. It may be the many black hole issue that's
yes.
to think about that.
So
Okay.
very last question in the back.
Yes, that's right.
That in itself is like a black hole feedback for the black hole, because it eventually regulates the maximum.
Right.
So what happens when you turn off this black hole feedback that limits the growth rate of the black hole?
Okay. Good point. I do not know. I mean, if I venture a guess, I would think, because we put the cap at 10 times Eddington, so I would think that we really don't have much because looked at the distribution of the accretion rate and was really peaking at maybe tens of Eddington or maybe even with the hundreds of Eddington. So I wouldn't expect it to change dramatically. On the other hand, we have seen that it makes a difference just going from 1 Eddington to 10. So I can't really answer this, but it's a good question. Thank you.
Okay, so let's thank the speaker again, and we are back at